Welcome back to the Game of Drones. I'm Hal Cowan, and today in this episode, I'll look at how AI is used in drones today, focusing on the core technologies that enable perception, decision making, autonomy, and coordination on the battlefield. Firstly, perception is one of the most critical challenges in military drones operations. On the battlefield, a drone never has a complete or reliable picture of its surroundings. Instead, it depends on a network of sensors, GPS, inertial measurement, radar, and cameras, all of which are vulnerable to noise, interference, and deliberate jamming, as we've seen earlier. This is where AI-driven fusion of sensors becomes essential, and one of the most important tools enabling this is called the Kalman filter. The Kalman filter provides a way for a drone to maintain an accurate estimate of its state of position, speed, or orientation, even in environments which are highly contested. It works by constantly predicting the drone's motion using a physical model based off maths, and then correcting this prediction using incoming sensor data. The crucial part, which differentiates the Kalman filter from other filters, is its ability to assign different levels of trust to different sensors based on how uncertain these measurements are at any given moment. In a military context, this matters enormously. GPS signals may be degraded, while inertial sensor measurements may remain fast. The Kalman filter intelligently balances these inputs, relying more heavily on accurate inertial data during periods of GPS denial and re-anchoring these estimates when reliable external measurements return. This allows drones to continue navigating, tracking targets, or holding positions, even when individual sensors are compromised. Because the Kalman filter operates in real time and continuously adapts, it underpins many advanced military capabilities, from precision strike and surveillance to coordinated swarm maneuvers. Rather than simply reacting to sensor readings, the drone maintains a coherent internal model of the battlefield. So, in effect, the Kalman filter transforms unreliable sensor data into a robust situational awareness. This is a subtle but decisive enhancement of AI in modern drone warfare. Seen in this way, once a drone can maintain reliable internal estimates of its own state, the next challenge is interpreting what the estimated position actually contains. This is where computer vision becomes central. Computer vision is one of the key AI technologies enabling modern military drones to operate with increasing autonomy. At its core, computer vision is about teaching machines to interpret visual information in a way that is useful for decision making. For a drone, this means turning a continuous stream of images into an understanding of what is happening on the battlefield. This process begins with cameras capturing raw pixel data. AI models, usually based on deep neural networks, then analyze patterns in brightness, color, edges, and shapes across every frame which is captured. Through training on large datasets, these models learn to recognize visual features that correspond to objects like vehicles, buildings, or even people. Rather than viewing an image as a single picture, the system breaks it down into regions and evaluates each one for the likelihood that it contains an object of interest. Once an object is detected, the system draws a bounding box around it and assigns a confidence score. By representing this process frame by frame, the drone can track objects as they move, estimating direction and speed. This allows military drones to follow targets, monitor areas over time, and detect unusual activity without constant human oversight. In combat environments, visual data is often degraded by smoke, darkness, or even camouflage. So to address this, computer vision systems are frequently paired with infrared cameras, allowing the same detection process to operate on heat signatures rather than visible light. Overall, computer vision enables drones to move beyond passive surveillance by continuously analyzing and interpreting visual data. AI allows military drones to maintain awareness, prioritize threats, and support faster tactical decisions. While computer vision explains what drones can recognize in the battlefield environment, it raises a deeper question. How do these systems acquire such capabilities in the first place? The answer to this question lies in machine learning and model training. Machine learning is one of the key technologies enabling drones to operate with increasing autonomy. At its core, machine learning allows a drone to learn patterns from data and use those patterns to make decisions, rather than relying on entirely fixed, handwritten rules. Central to this process is model training, where algorithms adjust internal parameters so that the model performs reliably when exposed to new situations. Two of the most important learning paradigms used in drone systems are called supervised learning and reinforced learning. In supervised learning, model training is carried out using large datasets of labelled examples. Each input, such as an image or sensor reading, is paired with a known correct output. During training, the model makes predictions and compares them to the true labels, adjusting its parameters to reduce error. Over many iterations, this optimization process allows the model to extract meaningful features from the data, such as shapes or motion. Once trained, the model can be deployed on board a drone to identify objects or classify terrain in real time, a capability that is central to military surveillance. Reinforcement learning, the other type of learning model we discussed, involves a different training process. Rather than relying on labeled datasets, the model is trained through interaction with an environment. Often, high-fidelity simulations are used. The drone repeatedly takes actions, observes the resulting state, and receives a reward signal that reflects the mission objectives such as safety, efficiency, or speed. Training focuses on learning a policy that maps situations to actions in a way that maximizes the reward over the long term. This approach is well suited to navigation or obstacle avoidance where unfamiliar or hostile environments are common. Together, these training methods enable drones to learn perception and control behavior that can adapt to complex and changing conditions. Once a drone can perceive their environment and learn from data, the next step is actually taking action. This is where autonomous navigation and path planning comes into play. Autonomous navigation is a defining capability in modern military drones, and much of it relies on classical but powerful algorithms, one of which is called A-star. A-star is a search algorithm designed to find the most efficient path between 2 points while accounting for obstacles, terrain, and operational constraints. The theoretical foundation of A-star lies in how it represents space and evaluates possible movements. The drone's environment is modeled as a graph made up of nodes, where each node corresponds to a possible position the drone could occupy. Connections between nodes then represent feasible movements, such as flying forwards or flying up. For every node, A-star computes a cost function, where one term represents the accumulated cost of reaching the node from the start, and the other term estimates the remaining cost of reaching the goal, often using straight line or Euclidean distances. What makes A-star especially powerful is that as long as the heuristic term, does not overestimate the true remaining cost of the journey, the algorithm is guaranteed to find the optimal path. This balance between accuracy and efficiency allows A-star to search intelligently while avoiding unnecessary computation. In military drone navigation, this approach is invaluable. Complex terrain, urban environments, and restricted airspace can all be encoded directly into the cost structure of the map. As a result, A-star enables drones to not autonomously plan routes that balance efficiency and safety. Autonomous navigation allows individual drones to operate independently, but the most transformative developments emerge when autonomy is extended beyond a single platform. This leads to the concept of swarm intelligence. Swarm intelligence is based on a simple but powerful scientific idea. Complex, coordinated behavior can emerge from large numbers of relatively simple agents interacting locally without any central controller. In the context of military drones, this means that one drone can follow a set of basic rules and decision processes, yet the swarm as a whole can carry out sophisticated tasks such as area surveillance or target tracking. At the core of swarm intelligence is distributed decision making. Each drone operates as an autonomous agent with limiting sensing, computing, and communication. Rather than receiving instructions from a central command unit, drones exchange information with nearby neighbors and respond to their local environment accordingly. This local interaction model is what allows swarm systems to scale efficiently and remain robust under disruption. Scientifically, many swarm algorithms are inspired by biological systems. For example, flocking models are often built around 3 fundamental rules: separation, which prevents collisions; alignment, which encourages drones to match velocity and direction with nearby units; and cohesion, which keeps the swarm together. When these rules are applied iteratively across many agents, collective patterns such as flight formation, dispersion, or regrouping emerge naturally without explicit coordination. In military applications, swarm intelligence must also account for uncertainty and adversarial conditions. Communication links might be intermittent or jammed, so many swarm algorithms are designed to function with minimal information exchange. This decentralization is a critical advantage. If one drone is destroyed or loses contact, the swarm can recognize itself without collapsing. More advanced drone systems integrate learning-based methods, allowing drones to adapt their behavior over time. Reinforcement learning, for instance, can be used to optimize how drones space themselves or allocate tasks dependent on the threats that are present. Ultimately, swarm intelligence represents a shift in how autonomy is engineered. Instead of relying on individual, highly complex military systems, it increasingly exploits collective intelligence where the behavior of the whole system is greater than the sum of its parts. As these capabilities scale from individual autonomy to collective intelligence, they raise a profound question about control, responsibility, and the role of humans in warfare. Autonomous killing systems represent one of the most controversial applications of AI in modern warfare. These systems are defined by their ability to select and engage targets without direct human control. While they are often presented as a natural extension of drone technology, they raise a distinct set of technical, legal, and ethical problems that existing military frameworks are poorly equipped to handle. A core issue is the accountability gap. When an autonomous system makes a lethal decision, responsibility becomes difficult to assign. The outcome of an attack may be shaped by training data, software updates, sensor noise, or even unexpected environmental conditions, rather than a clear human command. From a scientific perspective, machine learning systems operate probabilistically, meaning errors are inevitable. There is also a problem of unpredictability and escalation. The autonomous weapons respond to real-time inputs at machine speed, interacting with other autonomous systems in complex environments. Small misclassifications or unexpected behaviors can rapidly cascade, increasing the risk of unintended escalation without meaningful opportunity for human intervention. For these reasons, many argue that governance is essential, ensuring meaningful human control, restricting fully autonomous targeting, and developing international legal frameworks which are seen as critical steps in the future of drone warfare. Governance is not about halting technological progress, but about setting limits that preserve human judgment over life and death decisions in warfare. So that marks the end of the final episode of Game of Drones. We hope you've enjoyed the last 4 episodes, and we hope that you found something interesting out of it. Many thanks for listening. Bye.